Welcome to The Explainer. Today, we're diving into the epic story of electricity, from a mysterious, ghostly spark to the invisible force that, well, powers our entire modern world.
Just try to picture that for a second. It's almost impossible, isn't it? But, that was the world back at the dawn of the 18th century. Our story really begins when this invisible force was treated more like magic than science, a spectacle that both amazed and, frankly, terrified people.
So, our story kicks off not with some practical invention, but with something nobody on Earth had ever seen before. In a darkened lab in London, a strange, ethereal glow appeared, hinting at a power just waiting to be understood. So, what was the reaction? Well, it was extraordinary. You have to remember, in an era where natural events were often seen as acts of God, a mortal man creating light with his bare hands was almost beyond belief. This beautiful, haunting blue glow, it seemed alive. And just like that, electricity became an overnight sensation. But the question remained, what on earth was it?
For decades, believe it or not, this new force was basically the ultimate party trick. Electricians, as they were called back then, would go around delighting high society. They'd do things like lift feathers with a charged glass rod, give guests little zaps for a laugh, or for the grand finale, light a glass of cognac with a spark from their fingertip. There was even a trick called the electric beatification, where they'd create a halo of sparks around someone's head. Wild stuff.
But while the crowds were laughing, a few curious minds started asking some deeper questions. They saw something more, a fundamental force of nature just waiting to be understood. And that shift from spectacle to science really began when one man discovered a basic rule about how this force actually moves.
Okay, so to control electricity, you first have to figure out its rules. And the first huge breakthrough came from realizing that not all materials are created equal when it comes to this invisible force.
So this guy, Stephen Gray, he makes this critical discovery. What he did was he suspended a buoy from the ceiling with silk ropes. He found that an electric charge could zip right through the buoy's entire body, acting as a conductor, but it was stopped dead by the silk ropes, an insulator. This simple distinction is a principle we still rely on in every single power line crisscrossing the planet today.
So, okay, we get how it moves, but how do you contain it? It was just this fleeting, momentary flash. The next great challenge was figuring out how to, bottle this power. And that puzzle was solved by a complete accident in a Dutch university town.
The inventor, a man named Peter von Musschenbroek, was literally trying to pour electricity into a jar of water. He accidentally held the jar while touching the wire, and bam! He got a shock so powerful he thought it was going to kill him. And just like that, he'd accidentally invented the Leyden jar, the world's very first capacitor, a device that could store electrical pressure, or what we now call voltage.
But here's the thing. Nobody actually knew how it worked. It took the rational, logical mind of Benjamin Franklin to figure it out. He saw it less like some magical fluid and more like accounting. An excess of this electrical stuff was positive, a deficit was negative, and nature always wanted to balance the books. This was a huge leap, seeing electricity not as something you create, but as a fundamental balance in the universe. And this simple but powerful idea just completely demystified electricity. Franklin then used that same logic to tackle one of nature's most terrifying shows, lightning. By proving that lightning was just a giant version of the sparks from a Leyden jar, he took this thing, this wrath of God, and brought it right down to earth, into the realm of human understanding and eventually control. All right, so we could understand electricity and we could store it in these short bursts. But the next massive leap forward required creating a continuous, steady flow of it. And this whole new chapter was kicked off, believe it or not, by a pretty intense rivalry over twitching frog legs. Yeah, you heard that right.
On one side, you had Luigi Galvani. He saw that a dead frog's leg would twitch when he touched it with two different metals. He was convinced he discovered a special animal electricity, a kind of life force. But his rival, Alessandro Volta, he wasn't buying it. He argued the frog's leg was just acting as a detector. The electricity wasn't coming from the animal, it was coming from the metals themselves.
So, to prove Galvani wrong, Volta starts stacking these discs, copper, then acid-soaked cardboard, then zinc, over and over again. What he created did way more than just win an argument. This voltaic pile didn't just produce a momentary spark, it generated a steady, reliable flow of charge. He had just invented the first battery, and with it, the electrical current. And that continuous current, that was the key that unlocked the next door.
With it, the absolute genius Michael Faraday discovered that an electric current creates a magnetic field around it. He proved this invisible force was real, and by harnessing it, he was able to convert that electrical current into continuous motion. He had invented the first electric motor.
Okay, so now we can generate electricity and make things move. Awesome. But a huge new problem pops up. How do we get this amazing power from where it's made to where people actually need it? This very practical question would light the fuse on one of the greatest rivalries in the history of invention. On one side, you've got the world-famous American inventor Thomas Edison. He championed direct current, or DC. It flows in just one direction, kind of like water in a pipe. But his system had one massive, and I mean massive, flaw. The power faded fast. It couldn't travel more than a mile from the power station.
And on the other side? Well, you've got Nikola Tesla, a brilliant, visionary inventor with a much better idea: alternating current, or AC. See, AC reverses its direction rapidly, which means you can step up its voltage to travel super efficiently over long distances, and then step it down to be used safely in homes. What came next was a bitter public battle. Edison, terrified his DC empire was at risk, launched this vicious campaign claiming AC was a deadly menace.
But in the end, the science was just undeniable. When a massive power plant was built at Niagara Falls, it was Tesla's AC system they used to send power all the way to cities like Buffalo and New York. AC had won. And that victory, it paved the way for the vast electrical grid that powers our entire world today, all built on the genius of a man who, tragically, died almost broke.
So, after this incredible 200-year journey, what are the big takeaways? Let's quickly recap the fundamental rules of electricity these pioneers figured out, rules that are running every single device you use today.
These 5 simple concepts, they really build on each other. First, you've got conductors and insulators. Then there's the whole idea of positive and negative charge. From there, you get the relationship between electrical pressure, which is voltage, and its flow, which is current. Add to that the deep link of electromagnetism, and finally, the big AC versus DC choice that wired our world. Every light bulb, every smartphone, every supercomputer operates on these 5 core principles.
But for all our amazing progress, we still face a huge, fundamental challenge: electrical resistance. Think of it like friction for electrons, wastes a staggering amount of energy. About 1/5, 20% of all the power we generate is simply lost as heat as it travels through wires. It just vanishes.
So, the holy grail, the next giant leap, is finding a material that can conduct electricity with zero resistance at room temperature, a superconductor. Finding one would just unleash a revolution, on par with the invention of the battery itself. We're talking ultra-efficient power grids, levitating trains, quantum computers. The story of electricity is far from over, and its next chapter is just waiting to be written. Thanks for joining this explainer.